Well, good afternoon. Good afternoon. It's great to have so many of you here today. We're all in, I'm certain, for a treat. And we all look forward to a lively Q&A as we normally do with our speaker right after his lecture. Let me begin with some context on the Compton Lectures. In 1957, MIT established these Compton Lectures to honor the memory of MIT's 10th president, Carl Taylor Compton. He served MIT as president from 1930 to 1948. Do the math, that's 18 years. Guiding the institute through two difficult periods, the Great Depression and World War II. He served 6 more years as chairman of the MIT Corporation, our board of trustees, until his death in 1954. During his presidency, MIT went from these great outstanding technical schools for training hands-on engineers to the great global university we have today. He did so by bringing science to MIT. He's the president who did bring science and treated as an equal partner to engineering. He himself was a physicist. During World War II, he helped invent the partnership between the federal government and America's research universities that we have enjoyed. And that has been instrumental in driving a nation's economic growth for more than 60 years. He was known for the scope of his understanding, his integrity, and his commitment to public service. And it's fitting that we honor his legacy today with a speaker who embodies those same qualities, and that is Dr. Francis S. Collins, the director of NIH. As director of NIH, Dr. Collins oversees the work of the largest supporter of biomedical research in the world, covering the whole spectrum from basic to clinical research. As a physician geneticist, he's known for his landmark discoveries of disease genes and for his leadership of the International Human Genome Project. MIT researchers played an important role in that effort, and the project ended with the completion of a finished sequence, as we all know, of the human DNA instruction book. In recognition of that accomplishment, Dr. Collins, along with Princeton's David Potstein, an MIT graduate, and Eric Lander received the Albany Medical Center Prize, which is often referred to as America's Nobel. Dr. Collins has written a number of books on science, medicine, and spirituality, including the New York Times bestseller, The Language of God, a scientist presents evidence for belief. He's an elected member of the Institute of Medicine and the National Academy of Sciences, a recipient of the Presidential Medal of Freedom, and a recipient of the National Medal of Sciences. And he's also well known in scientific circles as a rock star. Playing guitar at TED-Med, Stand Up to Cancer, Rock Stars of Science, and other venues. This afternoon, we're delighted to welcome to MIT a champion of innovation in medical research and a brilliant advocate for research and development in the life sciences. Please welcome Dr. Francis Collins.
Thank you, President Reif, for such a kind introduction. Good heavens, this room is amazingly full with all of you people standing in the back. I feel badly for you already, but I will try not to carry on so much that you wish you were somewhere else. And if you do, you're sort of near the back, you could probably slip out. But it is a great pleasure, a privilege to be in an institution that has contributed so much to science across many different disciplines. And certainly, for me now, as the director of NIH, an institution that is contributing enormously to the grand adventure we are in the middle of in terms of understanding how life works and how disease sometimes can occur. This is the century of biology. Biology has found its way to join physics and chemistry as a truly digital science, and that is a wonderful experience for some of us who started out not being quite sure it was going to get there, and now I can see all around us, particularly in the work that all of you are doing, just how remarkable a time this has become in terms of our ability to take apart all of the parts list of how life works and figure out exactly what some of those mechanisms are all about. But let's not be too confident that we have it all sorted. There's still a great deal of work to do. I had a great time today meeting with some of the senior leaders at MIT over lunch and some of the researchers after that in a vibrant discussion about areas of their interest. And I'm particularly looking forward to meeting with students after this particular presentation and the Q&A. Such an amazing group of faculty, students, trainees who are here. I want to give particular recognition to a special person who is also here. Dr. Carola Eisenberg, who's sitting in the front row, who's now totally embarrassed by my having mentioned her, served as the first woman dean of students at MIT some years ago, about 40 to be exact. She's going to get me for that, I can tell already. Well, what I wanted to do, in the spirit of the title of this, is to say something about what I see in a somewhat arbitrary, personal way as some of the exceptional opportunities that now surround us in biomedical research. But there's always a risk in doing this because I will only be able to mention a few. And some of the areas that I don't mention are equally exciting compared to the ones that I do, so don't feel badly if somehow I seem to have overlooked the area in which you are personally spending your time. Because there's hardly an area of biomedical research that I cannot point to now and say is really full of potential, full of excitement. One of the great joys of being the NIH director is to be able to look out over the whole landscape of biomedical research and see what's happening. And if you read my blog every Tuesday and Thursday, and I'm sure you do, you'll see, because I try to write twice a week about something that's just happened in the research arena that I thought was particularly enlivening. And it covers a wide range from basic to clinical and across many different kinds of diseases. So I'm going to try to do that, and I'm going to try to do that in a reasonable period of time. And I'm going to go, I hope, in a fashion that people who are not expert in any of these particular areas will still be comfortable with the way in which they're presented, because I know this is a diverse audience, and this is the cultural lecture, and I hope, therefore, this has recruited people into this room who would not consider themselves on a daily basis as working at the bench or doing some other kind of hands-on science. So here we go. NIH is, as you heard, the largest supporter of biomedical research in the world with a dual mission: the pursuit of fundamental knowledge, the basic science part of what we do, but the application of that to extend healthy life and reduce illness and disability. We had an interesting discussion at lunch about exactly how do you do the balance right here between basic curiosity-driven science, which has been the mainstay of success of the American biomedical research enterprise, and more applied or translational efforts. And we talk about that every day at NIH, I can tell you. And I wish that we had more resources so we could do more of both. Right now, things are, in fact, at a historically difficult time as far as the resources. But I'm not going to focus on that much at this point unless you want to discuss it during the Q&A. I'd rather talk about the exciting science that's now possible. NIH funds scientists across the US, including right here at MIT, and not to be too specific, but you guys are consuming $103 million of taxpayers' money, at least you did last year, and I have a feeling it's not going to go down this year because of some of the things I'm about to tell you about in terms of new programs where MIT has turned out to be very successful in being highly competitive for NIH grant awards. And it is, in fact, I think appropriate that over the course of time, MIT has become a successively larger grantee of NIH as more and more of this institution has been focused on the biological sciences. The impact of research over these years can be seen here in this diagram of what's happened to life expectancy, steadily rising since 1970. A lot of that is because of reduction in cardiovascular deaths, now 70% down in the last 60 years. Stroke deaths down by 70%. Cancer death rates, although this is hard fought, are in fact now falling about 1% per year. And if you want to do an economic calculation of that, that adds up to about $500 billion each year from the basis of those increases in survival. And just to pick another dramatic example of how biomedical research has totally transformed the way in which we see a particular disease, many of you in the room don't remember when HIV diagnoses were basically a life sentence and that you might have perhaps 12 or 18 months and that was going to be it. And now somebody diagnosed as being HIV positive in their 20s with appropriate antiretroviral therapy can expect to live almost a normal lifespan. What an enormous change has happened there in the course of just a couple of decades. So I'm going to break down these opportunities into 5 themes and give you a couple of examples under each one. Again, not trying to be exhaustive in any way, because that would be impossible in the space of time that we've got available. But let me start out with sort of basic science issues, and I'm particularly focusing in the basic arena on technology development because those have been so instrumental in providing advances across the board. Don't get me wrong, there's lots of great basic science that is not in the business of doing technology development, but I think we all benefit when those technologies are developed and then distributed. One of those, which is now very much in the forefront in terms of an area where technology is ready, I think, to push us into new territory, is the BRAIN Initiative. Announced by the President just a little more than a year ago, this ambitious, some would say audacious idea that we might be able to understand how the circuits in the human brain do the amazing things that they do. Recognizing the complexities here are really quite daunting. You have 86 billion neurons in between your ears, and each one of those has maybe hundreds or even 1,000 connections. And the idea that we are bold enough to imagine we could understand how such a structure could work maybe seems a little outside the possibilities that we would have thought even imaginable 5 years ago. Some people even said that maybe our brains are not complicated enough to understand our brains. Think about that. Well, probably on their own, that would be a problem, but given all the other tools we can bring to bear on this, and that would certainly include computational modeling, maybe we're just brave enough to tackle this. But first, we have a whole lot of things we need to understand that we really don't understand. We really don't know exactly how you lay down a memory and retrieve it. We don't know how it is that you initiate a voluntary motor movement. We don't know how you, in fact, process information that's coming at you right now. How you recognize the voice of somebody down the hall that you haven't seen in 5 years and know immediately who that is and brings up all sorts of images. We don't know how that works, but we're determined to find out. So as part of this BRAIN Initiative, NIH convened a remarkable group of visionary neuroscientists led by Corey Bargmann, Rockefeller, and Bill Newsom from Stanford, and came up with a proposal, which I would encourage you to look at if you've not seen, which is up on our website, which is basically a 10 to 12-year plan about how we're going to figure out how the brain works. It has several priority areas. One is to really identify all the diverse brain cell types. We don't know them. We lump things together that are probably quite different. To build maps, circuit diagrams that vary in resolution, and then to figure out how those circuits actually work in real time, the dynamic picture, and to figure out causality. How is it that various activities connect to various behaviors in a way that you can infer causality? This should lead us to the ability to identify fundamental principles, which we still lack. Somebody at lunch today said neuroscience, at least understanding the brain, is in the pre-Mendelian era in terms of our lacking of basic principles about understanding how this works. That may be a little bit of a pessimistic view, but we got a lot to learn. We can all agree to that. And of course, a lot of this is going to be technologies that need to be developed and distributed and ultimately applied in a way that helps us both with normal function and ultimately to understand brain diseases. But make no mistake, this first pass, this first set of opportunities of the BRAIN Initiative is largely about technology development, and it's largely about normal function. Because if you really want to understand autism or schizophrenia or traumatic brain injury or epilepsy, you have to recognize that we lack that kind of foundation of normal function, and it's really getting in the way of progress, so we ought to turn our attention to that. So the first awards were announced by NIH in our part of the BRAIN Initiative. $46 million, 100 researchers, 15 states, 3 nations, 58 projects, And you'll be happy to know, I think, that when the dust all settled on where those went to, NIH gave 6 of those 58 to MIT. No other institution got that many. So you guys are really lined up here to take advantage, and you can see some of the themes that are being mentioned here. Again, this is a long-term investment. In my mind, this should ramp up over the course of the next few years to something like $500 million a year in support, not replacing what's already being spent on neuroscience, but adding to that and extending over the period of 10 or 12 years. Another area of basic science where technology has helped a bit is something I know a little bit about, the Human Genome Project, which happily Despite a rocky start, where again, many of you in the room may not realize that a lot of people in the scientific community were quite strongly opposed to the Human Genome Project when it was first announced. Fortunately, some technologies got invented, things went pretty well, but now we have this problem of it's easy to sequence a genome, it's a lot harder to figure out what it means. And for that, we have lots of other efforts that have been underway, the HapMap project, the 1,000 Genomes project, ENCODE, all of these large, complicated, coordinated efforts between many labs, but making all their data available to anybody who wants to see it at the very earliest moment. I might say, just parenthetically, that the Genome Project did two things. It provided a sequence, a reference sequence of our own species. The other thing it did was to really promote the ethic in a way that had not been done quite at this level before. The data of this sort ought to be immediately made publicly accessible with no barriers to access, so that anybody with a good idea could start using the information immediately. And that's what we did with the Genome Project, releasing the sequence fresh off the machines every 24 hours. And I think that is the right ethic for projects of this sort, and we're of course now promoting that in many other fields as well. Cost of sequencing has remarkably fallen over the course of these last few years. That's a log scale on the y-axis. Back at the point where we were just finishing the human genome, it would have cost us about $100 million to do the second one. Now that is down roughly to about $4,000, $5,000, and the vaunted idea of reaching the $1,000 genome is certainly within reach, some would say, in the next few months, given now the latest generation of machines that are coming on board, and we have not in any way seen the limit to that. We can continue to drop this substantially without running into any collision with the laws of physics. So there will be, I am sure, a time in the near-term experience of those of you who expect to be in science over the next 10 years, where the cost of sequencing a human genome really doesn't seem like such a big deal. It will drop below 1,000, maybe it'll get to 100. The big challenge, of course, will be the interpretation, not the actual determination of the A's, C's, G's, and T's. Now, of course, that is being applied in lots of important and interesting ways. Being here at MIT with a remarkable focus on cancer research, and with Tyler Jacks talking to me a little bit about that at lunch today, a big part of this has been the ability to tackle cancer in a systematic way. Until we had the ability to look at complete genomes, we were basically guessing which of the genes in the genome might be involved in cancer, or using some functional analyses to try to determine that. And we made a lot of progress, but we certainly could not say we had the whole list. Now with the Cancer Genome Atlas having provided analysis of many different types of cancer, including the ones that you see here, we have a much more comprehensive idea about all the ways that a good cell can go bad. And one of the things we're certainly learning is that our taxonomy of how we describe cancer, which tends to be focused on the tissue in which it arose, may need to give way to a taxonomy that's based upon the molecular defects that are present in a particular tumor. And one person's colon cancer may be more like somebody else's breast cancer than it's like a different patient's colon cancer, just because of the way in which the pathways involved tend not to pay much attention, at least not that much, to which particular tissue the cancer arose in. And of course, this has provided us with remarkable opportunities to identify new pathways that are appropriate for drug development. And there are now something close to 1,000 small molecules and biologics that are in various pathways in the direction of targeted therapy for cancer, based upon this knowledge of what is really going on at the genomic level with this particular disease. This has presented us with another sort of major challenge. And that's not just for cancer, but it's one of the more dramatic examples, and that is the amount of data that's being generated. Similar problems happening in other spaces. They will happen in a big way for the BRAIN initiative, but when you look at where the Cancer Genome Atlas data flow has gone, you can see for the numbers on here, 20 terabytes of data a month, more than a petabyte now. Used to be a decade ago where biologists complained about their data problems, and the physicists sort of looked at you like, oh, little one, you'll get by. And we have achieved credibility now in that space, given the size of the data that's being generated, and it's only going to go dramatically upward. As a consequence of that, I've recently hired and created a new position at NIH, the Associate Director for Data Science, and hired Phil Bourne, who's a remarkable data scientist from San Diego, formerly editor of PLOS Computational Biology, to come and help us organize what we're trying to do across many different projects, many different institutes in this space, including, he is hoping to set up something like a data commons, where data and metadata from a wide variety of experimental systems can be placed where you can find it and where you can compute on it and where there is some kind of attention paid to standards so that you can make sense out of it. A big challenge, to be sure, and one we will need everybody's help on, but one that we have to tackle. I think you could already say we're a little behind where we should be in terms of our plans to manage the big data challenges of biology, and we need to move quickly to catch up on that. Because there are lots of other kinds of data we need to think about. Nature and Science are putting it on the cover, and we're talking about genomic data just now, but we could also be talking about lots of other omics, imaging information, phenotype information, exposure data, clinical, now that electronic health records are coming along and are increasingly possible to link up together because there's efforts being made to make them interoperable. The Patient-Centered Outcomes Research Institute is trying to set up a national network that might have as many as 100 million patients involved in it, all of them with electronic health records and the opportunity for obtaining consent for research. Imagine what you could do with a data set that large, already created as a foundation upon which you could land all kinds of interesting clinical questions and carry out both observational and interventional studies. It's time that we had the chance to do that. We're a little behind in the United States because of our chaotic healthcare system, but we might be able in the current system to do something about that. All of that's big data challenge, to be sure. And so we have not only hired Phil, but also created a new program called BD2K, Big Data to Knowledge, which aims to do a variety of things to facilitate the advances that are necessary here. Developing new analytical methods and software, lots of opportunity here for computational biologists to put forward new ideas that we need to have pursued. Training needs to go in a much, I think, more aggressive way so that no graduate student in biology gets through a doctoral program without becoming facile in computational approaches. Otherwise, I fear those students will not find themselves competitive in the future. And we're setting up centers of excellence, about 10 of them, to address some of these issues. All of that just getting started earlier this month. Well, that was a bit about basic science, but again, I focused rather heavily on the technology and the data issues. Again, let me say as loudly and clearly as I can, NIH deeply values the basic science enterprise, including investigators who are not working in big teams, but who have a good idea that they want to pursue. There seems to be a rumor out there that we're only interested in translation. I want to scotch that right here. In fact, as I said earlier, the bedrock of much of what we have learned over the last many decades comes from that basic science investigator who is driven by curiosity to understand something. We would not have CRISPR-Cas, for instance, if that was the only kind of thing we funded. All kinds of things come in the most unexpected way from basic science. But of course, we are the National Institutes of Health, and so we want to be sure that basic science set of discoveries gets translated. And here we have both an opportunity and a responsibility to try to do something because the need is great. This diagram shows you the accumulated number of disorders for which we believe confidently we understand the molecular basis. And you can see that started up rather dramatically in the 1990s and continues maybe even with a little acceleration in the last year. And much of this is because these are rare genetic disorders, and if you have the ability to sequence the genome, nowadays, even with one family, you may be able to figure it out. And so you can see this has risen up to close to 5,500 disorders. That's great. That's good news. That means we can make diagnoses. How many of these conditions actually currently have a therapy that works? That's not so great. 500. So there's a huge gap between what we know and what we're able to do. And that seems like an opportunity not to be missed, but it's hard. It's really hard. These may be perhaps some of the most attractive places to invest our translational efforts because we do know what the target is, but obviously that's a long way from having a therapeutic, a small molecule, or a biologic that is going to solve the problem. And the problem is a tough one. You've probably seen diagrams like this about just what the traditional pathway looks like in going from the molecular understanding of a disease to having an FDA-approved drug. And you start with a very large number of candidate compounds, and that shrinks back as you do increasing testing And maybe then you'll have some that make it through and get an IND, and the FDA approves it for a clinical trial. And ultimately, if all goes well, you may get a drug approved. But notice at the bottom on the x-axis here, we're talking about 14 years as the standard timetable. And the cost, because you have to pay for all the failures, to be honest about this, and the failures are going to be 99% of what you started with, maybe more than that. The cost of a success is in the billions. We don't have that much money to treat those 5,000 diseases that are urgently looking for answers. So we got to come up with strategies that will improve the success rate and shorten the time. So why does it take so long? Well, a lot of reasons for that. Maybe I'll just mention one, but first I want to tell you what we're trying to do at NIH in a way to catalyze some attention to those systematic barriers, and barriers that are probably familiar to many of you, but not all. How do we do that? And how do we, as a publicly funded institution, identify barriers that are not going to get solved by the private sector, who are in this business, of course, to win, but those systematic barriers that no single company is going to tackle, but perhaps in partnership with the NIH, we could do something. And that's what NCATS, the National Center for Advancing Translational Science, is all about. It's only been around now for about 2.5 years, but I think it's pretty interesting to see the way this is taking shape. And I'll just give you one example. One of the things that holds us up in terms of this development process is to figure out whether a drug is going to be safe and effective in a human being before you give it to them in a clinical trial. And you'd like to have really good data before you subject a volunteer to a new compound that's never been in a human body before. You'd like to know it's going to work, and you'd like to know it's not toxic. How do we do that now? Well, we have all sorts of models, cell models. Ultimately, FDA will require you at the present time to use animal models, some small animals, some large animals, to try to show that the drug at least isn't toxic. And it's slow, and it's expensive, and it isn't very reliable. We are different than mice and rats. We're different than dogs, and we're different than macaques. And if you really want to know if a drug is going to work, you'd like to be able to test it in a human system, but you don't want to have to test it in a human if you can help it. So the idea here, and this is a joint effort with DARPA, which is part of the Department of Defense, and with the FDA, is to develop biochips that allow you to screen for safe, effective drugs where you have human cells, but they're not in a human. They're on one of these biochips wired up with appropriate readouts to tell you whether what you've just added to those cells is making them unhappy or happy. A phase 1 set of awards from this program was given out 2 years ago to get started, and that was 12 projects to develop these 3D cellular microsystems representing human organ systems using a lot of what we've learned about stem cell biology, so that you can take in the most elegant system an iPS cell from an individual, differentiate it into whatever tissue you think would be interesting, put it on the biochip, and then you have not only a generic way of looking at safety and efficacy, you actually have you on a chip, a biological sensor that is specific to the individual. And you can even begin to do things like pharmacogenomics outside of people, which is pretty exciting to do. So 7 projects were funded to also explore the potential of stem cells to do this. And this went actually better than I think most of us had predicted possible. And so phase 2 awards were just given this year. And I think I need to highlight one of them because it happens to come to an investigator here at MIT who I had the pleasure of speaking with earlier today, Linda Griffith. So this is an example of the kind of thing that I would not have thought possible a few years ago. Basically, not only does Linda want to figure out how can you look at liver, human liver, in a situation where it's not in a patient, but it's on a chip, but it's behaving pretty much like liver, but how could you use this as a system to study metastasis and figure out what happens if you have breast cancer cells in that human liver? Well, this is what she's been able to do. Basically, what do you want? You need something that looks not just like a monolayer of hepatocytes. You want the architecture of the liver, which is a sinusoid. So how are you going to do that before you put it into your bioreactor plate here? Well, what you do with 3D printing, or a version thereof, is to make a scaffold that allows the framework of that sinusoid to be prepared in advance so the cells can land upon it and arrange themselves appropriately. And I'm way oversimplifying exactly what the magic is here. So you put those in the wells, and then you add your liver cells, and they find their way to the appropriate place. And then, because Linda is interested in cancer, you also put in some triple-negative breast cancer cells that will find their way into these sinusoids, and now you have a model of the kind of thing you'd really like to understand when it comes to how do you treat or prevent this kind of metastatic cancer. And Linda's sitting in the third row. I hope she's not grimacing too much at my description of her work here. We okay? Okay, thank you. I'm feeling better. And so the kind of thing you can see, here's an example where the pink there are those dormant breast cancer cells sitting there in the midst of a whole bunch of liver cells, giving you a chance to do experiments like this one, which is a heat map, showing you the differences that occur, whether the breast cancer cells are there or not, as well as a number of other features. I'm not going to try to explain that because I would probably butcher it, but I hope you get a sense here that this is a very powerful system now, both to look at the interactions between the hepatocytes and the cancer cells, but also then to test various interventions. So I'd call this at least a second generation kind of biochip, maybe third or fourth, and it's the kind of thing that I think is enormously promising for understanding biology and also for this kind of translational science to speed up the process of identifying what's a safe and effective drug. So, another area that I wanted to mention that we need to make the most of is our opportunity to find partnerships with the private sector to speed up this kind of translational science, given the fact that NIH's resources are quite constrained right now. And drug companies are, in fact, increasingly recognizing there are areas that they used to call competitive that really could appropriately be called pre-competitive. After 3 years of working closely with a number of heads of R&D of Big Pharma, we got a program started just a few months ago called AMP, the Accelerating Medicines Partnership, where drug companies and NIH investigators sat around the same table, came up with research plans, hammered out exactly what their milestones should be, agreed that NIH and the companies would share the costs 50-50, and agreed that all the data would be immediately accessible to everybody. That's not a model I think would have been possible half a decade ago, but it is now. The diseases currently focused on by AMP are 3 areas: Alzheimer's disease, type 2 diabetes, and autoimmune disorders, specifically rheumatoid arthritis and lupus. And over 5 years, $230 million are going to go into this effort. The companies who signed up, there are 10 of them, and not all companies agreed to support each project. They all had favorites, and a number of nonprofit organizations also joined this effort because they also saw this as a unique opportunity to see how we could work together. We are closely now seeing the scientists from both sectors pushing the agenda forward with a variety of very ambitious efforts. The Alzheimer's project, for instance, includes a component that is really doing systems biology on normal versus Alzheimer's brains, trying to understand all of the things that might be appropriate to consider as new targets, because we've certainly had a lot of focus on the traditional targets of amyloid and tau, and a need for additional ideas about networks and nodes seems very appropriate. The Alzheimer's project is also looking to be sure that every clinical trial that gets run by NIH and by the companies uses every available biomarker so that you can assess whether, in fact, the therapeutic looks like it's working, which right now it's a bit spotty about who does which biomarker, and it's very helpful to have everybody using the same set. The third in my set of panels here, my set of themes, is improving healthcare through science. And obviously a lot of that is what we do anyway. There's certainly a component there of understanding how comparative effectiveness of things that are out there already being used should be assessed. I just want to mention one example here, and that is the very pressing issue of antimicrobial resistance. Those of you who have been paying attention to this will recognize that this is a growing problem, not just in the rest of the world, but here. Estimates are 23,000 people died last year of infections from organisms for which we had no real effective antibiotics left. We have had very few new antibiotics in the last decade. Organisms are doing what they do when faced with evolutionary pressures. They're developing resistance. There's the possibility, which is very real, of transferring those from one organism to the other. There's concern about the overuse of antibiotics in agriculture is contributing to that, although it's hard to precisely nail that down. And so there's a pressing and increasingly urgent need to do something about this. And so just a month ago, there have been 2 major reports about what NIH and other agencies should be doing. We are ramping up our efforts as a result of that. You can see some of the things that we are doing on the slide. I just point out one thing in case you're interested in a prize of $20 million. One aspect which is very technology-oriented here is we really need a point-of-care technology that would allow you, when you see a patient in the hospital who has pneumonia or a urinary tract infection or sepsis, to know in 3 or 4 hours, do they have a highly resistant organism? Right now, you're lucky if you have that in 48 hours. Sometimes it's 72. By then, you're way behind where you wish you were in terms of recognizing what you need to do. So NIH and BARDA got together here, and we have announced this $20 million prize. The details will be coming forward shortly in terms of what you have to do to win, but I hope in this brilliant audience there might be some interest in this. At least $20 million usually gets people's attention. And I want to highlight, because it's fun to do this when you come to a place like MIT, a particular contribution to this from MIT, and that is from Timothy Liu and his recent publication just a couple weeks ago in Nature Biotechnology about a new approach to come up with antimicrobials using delivered RNA-guided nucleases. You can read all about it in Nature Biotechnology. Well, our most important resource is not instruments. It is not, in fact, even dollars. It's all of you. It's our biomedical research community. That has been the reason why science in this country has been so remarkably successful. And I recognize that this community is under some stress, even though I can argue persuasively that there has never been a more exciting time scientifically to work in biomedical science than right now. I can also admit that it is a particularly difficult time to get the resources together to make this happen, just because of the fact that we have lived through 10 years of flat budgets, which inflation has been eroding. So we're actually down now by about 23% in terms of purchasing power for research over where we were in 2003. And we should all be making the case every chance we get about the need to turn that around. And believe me, I do that in my many visits to Capitol Hill, and receive a fairly positive response from virtually anybody in the Congress or the administration. The problem is it doesn't translate into actions, and we're still seeing this continual slide in our ability to support research. So that means we both need to be really tireless in making the case for why this is a very important investment for our nation, both in terms of our health and our economy. But we at NIH, working with all of you, also have to be sure we're doing the right things in this circumstance to encourage the most exciting science to go forward and not sort of hunker down and wait for the clouds to pass. So I want to say a little bit about some of the innovative ways in which we are trying to encourage the best and brightest, many of whom seem to be here at MIT, about how to pursue out-of-the-box ideas. Because there is perhaps a bit of a tendency on study sections when presented with way too many proposals, considering the number that you're going to be able to be funded, to pick the conservative ones and not the risky ones. So we have whole new programs that you can only apply to if you have a wacky idea, and that's good. I love wacky ideas. And so here are 4 of them listed. I'll just give you examples of each of these. And they happen to be at MIT. What do you know? So for instance, Alice Ting, who you see there on the left, has an NIH Director's Transformative Research Award. And I wrote about that in my blog last April, if you want to go back and read about it. And on the right, a new NIH Director's New Innovator Award given to Kay Tai, who is studying something about how it is that the brain interprets sugar cravings. These are just 2 examples of the kinds of projects which might not have fared so well in the traditional review, but which fared very well in this approach. And just in today's blog, if you haven't already read it, I wrote about this gentleman, Aaron Meyer, who received an Early Independence Award. This is a program that I started myself when I first got to the NIH director's position, because it seemed to me that there were individuals, particularly independent-minded and gifted and ready to be unleashed, who were not well served by being asked to go from a PhD to a postdoc to eventually an independent position, but who are really ready to go straight on from the doctoral training into an independent position, an idea of which, frankly, was pioneered particularly by the Whitehead Institute, and we learned a lot from their experience and felt that it's something maybe that NIH could invest in as well. And so for each of the last 4 years, we've funded between 10 and 20 of these specific awards. It's very competitive, and you have to have a personal interview where the people doing the interviews are really pushing to make sure that the applicant has the ability to tackle a problem that's both important and to be ready to have things fail and figure out what to do next, because all of these are high-risk areas. Aaron's particular effort is to try to understand kinases that are involved in signal transduction, and particularly how they contribute to chemotherapy resistance. So that would be a good example of a pretty high-risk effort, but one with a great payoff. And again, I'm very excited. Every year I get to go and listen to the new awardees for the Early Independence Award, and it's one of the best days I have because it is really exciting to see what people are coming up with. We also want to do more than we have been able to do successfully in the past, to be sure that biomedical research is a career path that is being pursued and is being seen as welcoming by individuals from a variety of different backgrounds. Women, certainly also individuals from different ethnic groups, people from socioeconomic groups who traditionally have not had the same opportunities for the experiences in a real scientific laboratory that often is that sort of moment of deciding, hey, this is what I want to do. I created another position to try to do something at the highest level at NIH to move this forward, and that's by recruiting Hannah Valentine, a distinguished cardiologist from Stanford, as my chief officer for scientific workforce diversity. And we are now, just last week, announced a new bunch of grants that are aiming particularly to make it possible for individuals in universities that may not be like MIT, but have students who are really interested in research to have the opportunity in partnerships with research-intensive universities to do that, because right now many of them don't have that door open, and we think that would be a good thing. And also to provide more mentoring for students from traditionally underrepresented groups who may not benefit from the kind of mentoring network that occurs so naturally to some of us, and which can be very helpful in getting one over those many rough spots that happen when you are trying to do something very difficult, like become an independent biomedical researcher. And we're going to have a very critical evaluation component built into this. NIH has been supporting diversity training programs for a long time. I can point you to a lot of anecdotes about instances where they, I know, have done good things, but the data is kind of shaky, and we really need to have stronger evidence about how these programs are working. If we're going to continue to invest in them, we have to know what works and what does not. Finally, and this maybe is the theme which when I became NIH director, people were most surprised by, but I don't know why, is to focus on global health. The world's gotten a lot smaller and a lot flatter. Domestic is not the opposite of global. We are, in fact, all connected, and you can certainly look at the headlines of the last few months and see why I'm saying that with great confidence. So NIH does, in fact, invest across most of its institutes in research that has impact on a global stage. One example that I want to mention, which just got started a couple of years ago, and again, I will take some credit or blame for pushing this forward, is a partnership with the Wellcome Trust and the African Society for Human Genetics called H3 Africa, standing for Human Heredity and Health in Africa, to try to build network in sub-Saharan Africa where we're linking up institutions with each other, making south-south arrangements. Most of these institutions have a partner somewhere in the north, but they don't actually partner with each other. H3 Africa aims to do that and has actually gotten off to a pretty dramatic start with a biorepository, building up an internet connection between these institutions, and starting several projects on common diseases in terms of the gene and environment contributions, actually mostly on non-communicable diseases, which are the most rapidly growing area of morbidity and mortality in the developing world. But of course, I can't talk to you about global health, as I'm sort of getting close to the end of this, without talking about Ebola, which has utterly consumed the time of many of us at NIH, particularly my colleague Tony Fauci, who you've probably seen many times on the television if you ever turn it on, because we are very much in the center of trying to address what is clearly a major humanitarian disaster in West Africa. Ebola didn't just arise this year. It was first isolated in 1976 in an outbreak in the Congo. We know a fair amount about it, that it is spread by direct contact with bodily fluids. It is not transmitted by aerosols through the air, so it is different than influenza, thank goodness. We know the incubation period is somewhere between 2 and 21 days. That's why you keep hearing 21 days is magical here in terms of deciding that an exposed person no longer needs close monitoring. And there have been 24 outbreaks in Central Africa since 1976, totaling but less than 2,500 cases. The current outbreak in West Africa exceeds that by a factor of 2 and will undoubtedly take the lives of many more before we get it under control. Starting with a single case of a child who died of this in Guinea, and then spreading to Sierra Leone and Liberia. Now 4,922 deaths as of 3 or 4 days ago, and that number will no doubt climb the next time it is reported, with a concern right now about an increasingly hot area between Liberia, Guinea, and Côte d'Ivoire. Long-standing commitments were made by NIH, even though some people might have argued this is not a problem that the US should worry about. Still, clearly, if we have global health concerns, this was something to work on. And as far back as the mid-1990s, NIH was supporting efforts to develop a vaccine for this condition, something which we are now glad we were doing, but wish was just another year or so ahead. Lots of work done on molecular technologies, appropriate animal models, development of new antiviral strategies. In terms of vaccines, the two at the top of this list are the furthest along. The chimp adeno3 virus vector platform is the one which was developed at the Vaccine Research Center at NIH. This is a 5th generation Ebola vaccine. The first 4 generations did not result in a sufficiently vigorous immune response. This one looks very good in the animal model, which is the macaque, basically providing 100% protection against an Ebola infection protocol which otherwise kills 100% of the macaques. But macaques are not humans. So in order to know whether this actually works, it is necessary, and you can't skip that step, to do the appropriate clinical trial. On September 4th, we inoculated the first of 20 patients at the NIH Clinical Center with this chimp adeno3 virus platform vaccine. None of those 20 volunteers have sustained any ill effects, so it's, I think, fair to say that it looks so far like this is safe. And we will know in another month what kind of immune response they seem to have generated, both cell-mediated as well as antibodies. And that will be somewhat, but not completely, predictive about whether the vaccine is going to be effective in the real world. To know that, we have to do a randomized controlled trial. There's no way to skip around that. Now, some have said, oh my gosh, it's a crisis. You should give the vaccine to all healthcare workers and hope for the best. But there are certainly examples where vaccines have not only failed to be effective, but they've actually increased the infectivity of the virus. There's a particular example with HIV that sobered everybody up a couple of years ago. And you can also imagine the consequences. If you start giving out vaccines and people assume they're helping, perhaps they relax a little bit in the personal protective equipment, which is now your best protection against infected, and you might actually see an increase in the number of healthcare workers getting sick and dying of this disease. So we have to go through this step, and I think experts have concluded it's actually not ethical to skip the step. It's ethical to do this. But that means trying to mount a randomized controlled trial in Liberia in a situation of great social chaos. We have a team right now in Monrovia of 6 individuals led by Cliff Lane at NIH. This is his second visit there, setting up the logistics to do this. Cliff is reasonably optimistic that we can, in fact, get such a trial underway as early as December, but it is going to be an enormous stress to do so. The second one listed here, a VSV virus platform, is only a couple of weeks behind in terms of its testing. It has also now gone through phase 1 clinical trials, both at NIH and at Walter Reed, and is also looking reasonably good. My hope would be we could actually do a 3-arm trial in Liberia in December. The VSV virus vaccine, the chimp adeno vaccine, and a control arm. And the control arm would still have to be an injection. People have to not know whether they've gotten it or not, and that would probably be a hepatitis vaccine, because that seems like a reasonable alternative. We could have a long discussion about how best to conduct such a trial in a way that is completely ethical and above board, and those discussions have been going on. Meanwhile, of course, many people are getting sick and dying of this disease, and we don't have at the present time effective therapies for them. By the way, today is Jonas Salk's 100th birthday, so it's nice that we're talking about vaccines. ZMapp is this cocktail of 3 monoclonal antibodies developed over the course of quite a few years with NIH support, and which has been given to exactly 8 patients, and the supply is now completely exhausted. This also has never been subjected to a human clinical trial. It works great in monkeys, and it's synthesized in tobacco plants, which turn out to be very elegant, but not very scalable. And so until later this year, or maybe early next year, we will not have enough ZMapp to run a trial, and we all really want to do that. Brincidofovir is a drug that was developed for CMV, an adenovirus, seems to have activity in vitro against Ebola, but we don't know whether it's going to work in vivo, and trials need to be done there, but at least that's a compound that's been in humans before for other purposes. The Tecmira compound is actually an siRNA compound. And by the way, all of the top 3 here have been given experimentally to patients in the US who were brought here for treatment. But with n equals 1 or n equals 2, it's very hard to know with very sick patients whether any of these have helped them or not. You may read claims saying ZMapp saved lives. Well, most of the people who got it lived, but not all. And of course, we don't know what would have happened without that intervention. The mortality in West Africa for Ebola is about 60%, but we don't know what that would be if you had the opportunity for intensive care support of people who are mostly dying of dehydration and low potassium levels because of the profuse vomiting and diarrhea that accompanies this disorder. It's almost like cholera. So we need to push this as well. Meanwhile, of course, the Americans, being who we are, seem to have forgotten lately about West Africa and are totally focused on our grand total so far of 6 or 7 cases that have actually been here in the US. At the present time, exactly 1 person is infected with Ebola in the United States. That's Dr. Spencer, who's in Bellevue Hospital. So I do wish at times that we could, in fact, remember that the real crisis is not in Dallas, and it's not in New York. It's not at the NIH, although we have had our chance to take care of a patient. In fact, we had a very happy occasion last Friday with Nina Pham, who's the nurse you see in the middle of the picture, being released from NIH, cured of Ebola after an intense more than a week of basically support, doing all the right things for fluids and electrolytes, and now looking quite wonderful. So yeah, we have a lot, I think, to do to try to push both the American mindset and the American science in the direction of where the real challenges lie. It is good that a lot of scientists have rallied to that occasion. One of them wrote this paper and allowed me to write a blog about it just about 6 weeks ago. And this is an effort to use the tools of genomics to really understand what is happening with this outbreak. Are there multiple different origins? Because we know this virus survives over time in an animal host, probably a fruit bat. Is the fact that we're seeing this big outbreak in West Africa really just due to spread from a single individual? Are there multiple origins? The work that was done here documented the multiple origins can be excluded. This is a single outbreak, presumably arising from that first patient in Guinea in late December of last year. The person who did this work put all of the data immediately up in the public domain, even before publishing this paper in Science, which is a great credit to her. And that is Pardis Sabeti, who is an NIH Director's New Innovator Awardee. Pardis not only led this effort working with her colleagues in Sierra Leone, where she had been working on Lassa fever before Ebola broke out, she also did everything possible to try to include those authors as part of her paper, because they were full collaborators, even as they, in Sierra Leone, were facing the daily experience of more and more patients coming under their care and having them succumb to this terrible disease. And particularly heartbreaking, of course, is that not only patients are dying, but healthcare workers as well. And by the time this paper was published, just a few months after the work was done, 5 of the co-authors had already died of Ebola that they'd contracted themselves while taking care of patients with this disease. Their names you can see there, and this paper honors their memory. If you haven't read this story, you can read a lot more about it in the New Yorker in the issue that was just published yesterday about Pardis and her efforts in that regard. And I've known Pardis for a number of years because of her role in genomics. And by the way, she is an MIT person and very connected with what's going on here in her role at the Broad Institute. And not only has she been working on Ebola, she's also been part of this H3 Africa project that I mentioned a minute ago. And in the middle of what was happening in the course of June and July, while trying to figure out the pattern of spread of the Ebola virus, she was also hosting a number of investigators from Senegal and Nigeria who came here to Boston to learn something about the molecular approaches that they could use going back home to do surveillance for Ebola. And you may know Nigeria had a very close call shortly after that, and Senegal has already had a case. She hosted them and had the chance then to work with them. Meanwhile, her colleagues in Sierra Leone increasingly getting ill, and in the middle of all this, as she learned, while working with the folks with H3 Africa and actually writing a song with them, which I read about in this New Yorker, she found that her closest colleague, Dr. Khan, had died. A very powerful story indeed. And as I read this in the New Yorker a couple of days ago and read about the song that she had written, it occurred to me, this is a cultural lecture. This is an opportunity where we should, in fact, not only talk about hard science, although it's great to do that, but also reflect a bit about what our role is as scientists who are citizens of the world, that what we're engaged in is a noble enterprise. It's a grand adventure to understand how life works, to uncover principles that have eluded humankind for all time. But it is also an opportunity to alleviate suffering and try to reach out to those who need our help. And it seemed to me, therefore, what Pardis was doing here was a wonderful example of that. So I asked her if there might be a video of the song that she had written, and it turned out that there in fact was. These are a couple of clips from that video. This is the person to whom it was dedicated, Dr. Khan. And I would now like to ask you to listen to that video, which you will see includes the individuals from Senegal and from Nigeria who were there with her this summer here in Boston, all participating in a song which is not a dirge. It is a song about what's really important, about the one truth, about how we are all connected and about how we're all going to survive, but we have to depend on each other to get there. So if you could you roll that video?
We have to say
So if you thought that was just a spectator moment, think again, folks. It's the cultural lecture. We're going to all try to be really cultured here. So let me introduce Pardis Sabeti, the co-author of this song. And also, Bob Katsiafikis, the guitarist and co-author of the song. Bob? And by special arrangement, straight from their morning exams, we are honored to be joined by the a cappella group, the MIT Logarithms. And we wanted to be sure this was going to be participatory. And, you know, one way to do that is to do a quick little rehearsal, which is what we're going to do right now. So you heard the video, and you probably already have that chorus in your heads, and you will be there, at least in my head, for at least the next 6 months. So it's a good thing it's a really good song. So all that yeah, that's your part. And I know you can do it, and so we're going to try just seeing if we can run through that. A harmony is okay, but not necessary. Am I on? Are you on? Yes, it's coming? Okay. Okay, so it goes very simply. All you got to know is and yeah, and you're there. Here we go. Come with me now. Yeah, 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 yeah. Yeah. Come on. Yeah, 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 yeah. Do that. Come on. Yeah, 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 yeah. Yeah, 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 yeah. Yeah, 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 yeah.
Sounds good.
Okay, now, this first time the chorus comes up, because there's a little video being made here, so we got to be sure this is so structured. First time the chorus comes up, you can just listen, but the second time, encouraged by the logs, you're going to come in. And from that point, whenever you hear yeah, you're on. Okay, I got to say, this is really scary for me because I learned this song like 2 days ago, and anything could happen, but it's a good thing we have real musicians up here. And I'll try not to mess it up. So, are we ready? Okay.
1, 2, 3, 4.
Sitting here in this room, watching everything move. I do not know how this city was built.
We are forsaken to the sound, oh, that life that goes. But we were born to radiate. Yeah, 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 yeah. Yeah, 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 yeah. Yeah, 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 yeah.
And we are gathered on the ground, waiting for a sign to arrive, looking for the answers in the starry sky.
But we were home all alone, and we are the light. We think, we speak, we walk, we breathe the air. Yeah. Yeah, 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 yeah. Yeah, 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 yeah. Yeah, 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 yeah.
Yeah.
A lifetime that we write,
and we laugh, and we cry. pray, and we all love, and we dream, and we scream, and we strive, but the hunger will never die, and I'm here in this fight always. Yeah, 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 yeah. Yeah, 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 yeah. Yeah, 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 yeah. Lifetime, the one truth that I'm alive, and so are you. We are here, we are the proof. Yeah, yeah, yeah. A lifetime, the one truth that I'm alive, so are you. We are here, we are the proof. Yeah, yeah, yeah. A lifetime, one truth that I'm alive, so are you. We are here, we are the proof. Yeah, yeah, yeah. A lifetime, the one truth. A lifetime, the one truth. A lifetime, the one truth. Yeah, yeah, yeah.
Thank you all.
Francis, I can tell you that in the almost 60 years of Compton Lectures, we have never had anyone like this. Well, while we recover from this lecture and this amazing ending, I'm sure, Francis, right? I'm sure that you still are willing to entertain some questions or perhaps request for more songs.
I don't know about that.
So anyone who wants to, please join the line up at the microphones, and I'll be calling each of you to speak. Please go ahead.
Hi. So other than, I mean, you've answered this a little bit, but I want to know your personal and NIH, some of the ways other than music. Music seems like a good one, to draw support from U.S. politicians and people for the type of problems that are really hard to draw support for. So I know NIH basic science, that's one of the key things, but there's long-term preventative. Ebola, people are noticing it now, but I'm an infectious disease, and I sort of ignored it when it was only tens of cases instead of tens of thousands, even though it would have been good to be preemptive. Altruistic goals, global goals, daunting goals, where at places where you don't think there's any hope.
Wow. Well, I think the job that we all have is to be prepared at any moment to explain what we do and why it matters. I think the time where scientists could basically go in the lab, close the door, and say, well, that's somebody else's problem to make those explanations has gone by. That's certainly not the time we are now. I do spend a lot of my time talking to members of Congress, hundreds of them in the last couple of years. The good news is can't remember any of those conversations that really went badly. The case we have to make is so compelling in terms of an adventure to understand really important things about science. Most people can get excited about that. In terms of what it may teach us that will help in terms of health issues. And the economic argument, which is very strong. And for some participants in this conversation, it also helps to point out that America, which has led the scientific effort in biology for many decades, is not really able to say for sure that we could continue that if we continue to slip and other countries come back very strongly. That does get attention in political quarters. I'm not sure it's my favorite argument, but it's certainly in there as something we should be ready to say. My concern, and I shared this a little bit with some of the people today, is that I don't think the scientific community has a voice that's been heard as loudly as it should in terms of the value of what we do. Every other special interest, believe me, has no problem promoting the value of what they do. And frankly, most of them don't even come close to what you all do. But we're not very good at advocating for ourselves. We somehow sort of act as though that's a little bit uncomfortable and maybe even not proper. We need to kind of get over that. Not that we're going to become full of hyperbole about what we can do overnight, but to defend and explain what we do. I think that's part of every scientist's life now.
My name is Jesse Kirkpatrick. I'm a senior. Thank you so much for coming to speak to us, and of course for the performance. My question is about rare diseases. So the NIH does focus somewhat on rare or orphan diseases. I'm wondering, what is the incentive for the NIH to focus on diseases that don't really have necessarily the scope of these larger diseases that are more maybe financially viable or could affect more people, but to focus on these rare diseases that only affect a few?
So that comes up a lot, and of course, a big debate that happens every day at NIH is, are we using our resources as wisely as we could? Frankly, a lot of how we spend our resources depends on all of you and what grants you send in with what ideas. So we're not sort of deciding, okay, we're going to spend X dollars on rare diseases and X on common diseases. We have a way of steering it a bit with RFAs, but a lot of it is stimulated by all of you. I think one can make actually a very strong case that the study of rare diseases down through the years has taught us phenomenally important things that often have much broader spin-offs than just to those people who suffer from that disease. My own laboratory at NIH studies probably one of the rarest diseases ever described, Hutchinson-Gilford progeria syndrome, this dramatic form of premature aging. I think we might know of 200 kids in the whole world right now that have that disease, less than 100 in the US. And yet, it has taught us things about senescence of cells, as well as of individuals, that we would not have discovered any other way, in terms of a pathway that's probably active right now in all of you, but at a lower level than in these kids with progeria. And you can tell many stories like that. We wouldn't have statins if Brown and Goldstein hadn't decided to study rare patients with homozygous familial hypercholesterolemia, on down that line. So I think the case can be made very strongly. It can also be made, I think, on a humanitarian basis. If we completely define our portfolio based on what's a common disease, then what happens to those families with a rare disease? For them, it's not rare, it's their whole life. Are we going to rule out paying attention to that? We can't do that. But it is a tricky balance. You're right to bring it up.
Thank you.
Please.
Hi, I'm Jessica Sagers. I'm a doctoral student. And I love what you're doing here. Thank you for coming. I feel like kind of that you're preaching to the choir, though. We're all scientists, and we're all very excited about our work and very excited about biomedical science in general. Something that I've seen lately online and in different forums is distrust from the public, especially when it comes to, for example, the conspiracy theories going around about Ebola or about different diseases that as scientists we understand and we know how to discount, but how is NIH currently working to improve the communication gap between the scientists and the public?
Yeah, another great question. And you're right, there is a big gap, and some of the things that one sees in the blogosphere, or worse yet, the Twitterverse, can be really breathtaking in terms of their conspiracy opportunities or naivete. I mean, frankly, I think a lot of this is a comment upon how badly we have slipped in K through 12 education when it comes to teaching people about science, or even about how do you draw an inference from data that actually is going to be reliable, and that there's a difference between an opinion and a fact. That doesn't seem to be so apparent in cable news. You know, it's just, if it's your opinion, well, it must be true. It's true for you. Well, no, actually, it's not. If it's wrong, it's wrong. So we have a big problem here, just in terms of our culture, acceptance of perspectives. NIH's role is very much in this space. We spend a lot of effort trying to communicate what we know and a lot about what we don't know. And when you come to Ebola, for instance, the person that you've probably seen more than anyone else is Tony Fauci. He was on all 5 Sunday morning news shows 2 weekends in a row. I don't think anybody has ever done that before, trying to really put out the facts about what's happening domestically, what's happening globally. in a very clear way, if people are willing to sort of accept that as an expert opinion. But everybody's an expert sometimes. It's a cultural issue for us. It's a reflection of our educational problems. And we can help with that, but we sure can't fix it all by ourselves.
Thank you, Francis. We'll take the next 3 questions and we'll stop there. We have to stop in a few minutes, so we'll take the 3 of you. Go ahead.
Hi, this is Manolis Kellis. I was a freshman once, and they still haven't kicked me out. In computer science. So I'm a scientist, and I apply for grants, and we're all applying for grants, and we all have ideas that we think are great, and but we're all effectively competing with each other. It's a small pot, and my question is, can we take all that energy and translate it into a bigger pot? In other words, all of us scientists could, I don't know, make videos, make presentations, come talk to senators, come talk to congressmen. And when you talk to them one-on-one, they understand and they see both the economic potential as well as the sort of long-term impact. My question is, can we translate this, oh yeah, it makes sense at the end of this lecture, to yes, it will make sense still the next time I vote? In other words, some kind of a pledge or something that each of us can basically target our local politicians or individuals on a one-on-one basis, and sort of engage really the scientific community for the role of enlarging that pot, rather than just bringing the best ideas forward for a relatively small pot compared to many other things.
Yeah, I have to be careful because I'm not allowed to lobby the government, but there are organizations that I think are playing a pretty effective role here. The AAU, where President Reif is a prominent member, has a role to play there. FASB plays a role in a very important way. You should be encouraging and supporting them if you're not already. Certainly, Research America, which has been around for a while, has the attention of a fair number of people on the Hill. The new kid on the block, and one you probably haven't heard of, but go and look at their website, is called ACT for NIH, ACT for NIH. Just started a couple of months ago with a very intentional effort to try to spread this word in a fashion that has the greatest likelihood of being remembered. So have a look at that. But you can't do this sort of as a lonely voice, and you all happen to be in a town where this is sort of accepted as, of course, medical research is important. It's trying to reach out beyond your own boundaries through the mechanism of one of these organizations is often the best way to do it.
Thank you.
Thank you very much for your wonderful talk and beautiful song. I also want to thank for supporting my research as a postdoctoral fellow. I currently have a F32 fellowship, so thank you so much. And thanks to NIH for doing that great job.
Very glad to help.
And being trained as a scientist in molecular biology and biomedical engineer, at this point I'm interested to pursue federal employment opportunities. And being here in Boston, I couldn't find any jobs or something that can provide me some insight or extra training so I can combine my scientific expertise with some regulatory or decision-making processes. Do you have a program for postdoctoral fellows or for young scientists where you can link them with decision-making people so we can work for government and help to solve these problems as scientists?
Yeah, one that particularly mentioned is the AAAS has a fellowship program which is competitive but very well regarded. And they take 20 or 25 fellows every year, oftentimes postdocs who are looking for a way to get more engaged in the policy setting arena. I would certainly look at that. Certainly, though, MIT has some pretty powerful policy shops as well, and assuming you have bumped into those people, they might be able to point you to other things. But I would look at AAAS's fellowship. It's a wonderful program.
Thank you so much.
Okay, the last question, please.
My name is Andy. I'm the graduate student here at Biological Engineering Department. I just have a question about your view of patents and the role of patents in biological research. Just because lately, in the last few months, there's been a lot of discussion about whether patents are actually good for innovation. And I guess one of the key news is Elon Musk deciding to release its patents for a Tesla motor in the idea that that will actually spur on more innovation in that field. But for biomedical research, it seems that if you take away patents, you really drain a lot of the incentive for private sector to be involved in research. I'm wondering what's your view on that?
It's a great question. I think it depends a lot on the details. I think of patents sort of like toll booths on a road, that if you need to maintain the road, you probably ought to be sure you're collecting some funds now and then to make sure that happens. But if you put a toll booth every mile, Nobody's going to want to ride on that road. It's too expensive. It's inhibitory. Basically, I think when you make a decision about whether a patent is appropriate, it ought to be done on the grounds of whether, in fact, that patent is going to encourage the development of a product that the public is going to need, and that without that patent, that development is less likely to happen or it won't happen at all. And that is to say, patenting something very early in the discovery pathway, it doesn't fit that model and probably should not be something that we support. NIH actually has research guidelines about this. So genome sequences, for instance, which you may remember, there was a big battle about that back in the 1990s, sort of a gold rush to patent all kinds of snippets of DNA of no known function. That was a really bad thing, and we're glad that that now, especially with the Myriad decision by the Supreme Court, we're not going to have that happening anymore. I talked about Pardis's data on Ebola sequences. Those definitely should not be patented. They ought to be made publicly accessible. Pardis is running into some struggles there, getting everybody to agree to that, because there's patents on the one hand and there's secrecy on the other. And sometimes patents are a way to avoid secrecy because you have to disclose what you learned. But in many instances where we're talking about very early discovery, pre-competitive data, neither patenting nor secrecy makes sense. I mean, Benjamin Franklin, when he kind of came up with the patent law, had the idea, like just what I've said, that you need to have a way of providing incentive for a product development by offering a limited monopoly to somebody who'd made a discovery so that they would carry it all the way through to something for public benefit. It wasn't supposed to make them rich. It certainly wasn't supposed to slow everybody else down. But I think, especially in the last 10 or 20 years, we've slipped a bit in terms of having patenting happening at an earlier stage than would be really good for the public benefit, and pushing that back towards later stages, which is happening now, I think, more and more, is a good thing. But don't get me wrong, patents in the right space are critical. We would not have the products the public needs or devices if we didn't have patents to protect those inventions and make it possible to develop them all the way to the point that a public benefit occurs.
Francis simply stated you have been outstanding. Please join me in thanking him for his service.
Thank you. Thank you.